Another fine DigiKey morning to ya. We're going to shop for an accelerometer. So this is going to be for a persistence of vision light show that is going to be mounted to a machete. We want to make an American flag on this machete, just like the founding fathers intended. We're going to turn on all these LEDs as we arc in the air majestically to make the American flag. Old glory. Now, well, to do this, we're going to need an accelerometer because we need to know where we are. Now, acceleration, of course, is meters per second squared. So if you integrate over seconds, you're going to get velocity, right? If I count how much acceleration I've had in a certain amount of time, I'll get velocity. Now, if I count how much velocity I've had in a certain amount of time, I'll get position. And position is where we need to blink this LED. So, now I wish we could measure velocity directly, but just because of Einsteinian relativity and just frame of references, it's just not a doable thing, right? A closed inertial reference frame can only measure acceleration. Certainly not position. Don't be daft. We're going to find ourselves an accelerometer, and we're going to do the math. We're probably going to use a Runge-Kutta method. Do what you got to do, right, to make it in this world. We're going to use a Runge-Kutta method on accelerometer to... Now it's going to be in the sensors subheading. Sensors and transducers. I mean, we could do a gyroscope too. Let's not complicate things, right? As you swing a machete, you're going to rotate, but that is just that's not what I want. I want acceleration. Now, first thing we do, in stock, 100% of the time we check in stock first because you can't design on something that isn't there. Now, if you're looking for a part that's a little more esoteric, at least restrict yourself to active. Please. Do not do what I did with my first project and buy an accelerometer that immediately went out of style within a year. I had to redesign a whole board. A whole board. It was the worst. Okay. We got a lot of accelerometers here. Acceleration range. This is the maximum amount of acceleration that it can see. Now, without doing any sort of tests, I really just can't know. So, not knowing the range that's necessary, it behooves me to keep my options open. Now, when I say I keep my options open, that means I either have one footprint that can give me a lot of options. Let's say there was a plus or minus 1.5, a plus or minus 3, a plus or minus 6, a plus or minus 100, that all use the same footprint. I just need to buy a different part and just solder it on the same spot. That's a viable strategy. I can also just put two footprints down and just pick two accelerometers and only buy one of them. Board space is cheap. So let's see what we can do. I think the range is going to be the most important part. You know what? I'm looking at these filters, and I think the voltage supply is going to be very important. I want to keep this bad boy at 5. Now, am I able to do it? I'm taking a look at my microcontroller. Micro can go to 5, so we got some flexibility. I think I'd like to keep one single voltage rail. Let's keep it to 5. So anything that includes 5 in this range here, I'm going to go ahead and pick. Okay, there's one. There's one. Oops. There's one. There's one. There's one. And there's one. There's one. There's one. There's another. This takes a while, by the way. There's one. 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 Okay, these are just right out. That's not going to work out. 18 volts. What kind of circuit? How do I only have 5? Sorry, let me get rid of that acceleration range. I accidentally left one clicked. No wonder I only had 5. I really should have 54. So 54 is the number. That gives me ranges anywhere between plus or minus a half, 1.7, 100. That's a lot. 18. Good Lord. This is not really in order. Okay, plus or minus 2. It's a tough call. It's a tough call. Let's clear that. I don't want to marry any one of these in particular just yet. Oh, I could do any of these. Bluetooth, good Lord, no. All right, so let's do analog, I2C, SPI, SPI. All right, let's see what we get. I think Kionics is decent. I had a demonstration by their vice president a long time ago. He had an accelerator. He had like a little cube that if you shook it one way, it would turn the volume on something up. It would use it would read the accelerometer, notice that you were shaking it on a certain axis. Then it would, through Bluetooth, adjust the volume of the speaker. If you shook it a different way, it would change the track. It was very snazzy. I liked it quite a bit. But boy howdy, is that expensive. $11. I'd rather not. Let's sort by price. When in doubt, sort by price. $2. Memsic. Okay. I don't know Rochester Electronics, but that is an old school looking package right there. That's like a tall, fat T-SOP. It's called a 16 SOIC. Yeah, sure. Rochester. Oh, wow, this is a new design. Okay. These are all very expensive, but that's how it goes. Plus or minus 2 Gs. $60 Gs, 120 Gs. Wow, these can measure vibration. I mean, plus or minus 2 Gs makes me a little uncomfortable, but 22 feels like it's got a lot of margin to it. I might be picking the fat boy. Oh, gosh, these ranges are just all over the place. These prices just jack right up. NXP, they're decent. I got nothing bad to say about NXP. And I've heard of Memsic. I'm a little bit... Maybe I'll give him a shot. I don't know. The bandwidth is 10 hertz. Okay, so this is not like the fastest updating accelerometer, right? It's not the most dynamic. But it might be perfect. Because we're only going to take one swing. Well, that doesn't bode well, does it? Yeah, when your data sheet gives a 404 error, that's a bad sign. That's a bad sign. Okay, Rochester. Let's see what you got. Got a Kionics here. Let me say that I just want to border one. Get all these minimum quantity 4000s out of my way. Wow, we really go up. Really kicks up a notch here. Jeez. Oh, that's a good package. I like it, but man. Plus or minus 8. God, $30. What the heck? What did I do? What did I do to deserve this? Ugh. How are these all so expensive? Why are these all so expensive? And back in my day, it was like $7. These are insane. What did I do? Which one of these filters did it? Is it part status? Nope. They all run right up to $10. Output type? Nope. Shoots right up to $10 and then $30. Voltage supply? I doubt it. Oh, wow. Oh, wow. Okay. Huh. Ha ha. 3.6 volts. Oh, wow. So changing the voltage supply to 5 volts really... That really limited our options. I did not expect that. Look at this. There's so many Kionics pieces here. There's Worth. Oh, wow. Okay. So... 3.6 volts it is. Good lord. At least our micro can handle that. It can go down to 1.7, which is coin cell battery voltage. I like the fact that we get some flexibility here. That's really good. And XYZ, It's coming in standard. Love it. That means we don't have to worry where we position it. I like that. I2C, that's always a great interface. It's fast. It's simple. Not a lot of circuitry required. Just a couple of pull-up resistors. Kionics, I trust you guys. You're also pretty cheap. This MEMSIC guys kind of turned me off. Having a 404 error on their datasheet. That's not good. Sorry, MEMSIC. First impressions are usually the only impression. Okay. Kionics. Very cool. Tri-axis, 2 plus or minus 2G to 16Gs. Gives you flexibility. If you can change something in firmware, that's much better than buying the hardware, right? Don't switch out hardware, switch out firmware. Firmware you can change in a drop of a hat. A drop of a hat, yeah, sorry. No, it is drop of a hat. I thought that was wrong for a second. Okay, XYZ goes into a charge amplifier. Then you also get a temperature sensor. You get an analog digital converter that goes to a filter. So we're not going to... Okay. Then you have your I2C engine, which... You've got your address, your serial data, your serial clock, and your interrupt. I bet you address is a digital input to determine the address of it. So you either put it a 1 or a 0. It'll change the actual I2C address. So you can have multiple of these. Of course, interrupt is probably a pin that's an output that this chip will use to notify you of some sort of change, whether a sample's ready or a threshold has been crossed. And you got SDA and S-clock, which are just a standard part of an I2C interface. And you got a couple of voltage rails. That's cool. Whatever. Who cares? Let's make sure this VDD and this IO VDD are similar in what they require. Yep, they are. All right, cool. They both want 3.3. All right, I'll give you 3.3. I'll get a linear rig. All right, sorry. I'll get a switching regulator in here. Typical startup time. I don't care. I want this guy on all the time. And now if I want this accelerometer on all the time, it's going to be consuming battery, right? Now, I've got a lot of juice in the battery I'm using. But here we go. High resolution. It's going to use 155 microamps. That's pretty small. So let's say you had just to give you a reference, if I had a AA battery, amp hour. Okay, zinc chloride battery store around, okay. Alkaline, that's more realistic. Let's say it's the upper level of alkaline, so 2,850 amp hours, right? Amps is charges per second. If you multiply that by time, you get total number of charges. So let's say you use 2 of these in series to give you a 3.3 volts, right? So you've got 2,850 amp hours, right? So if I wanted to do the math here and find how many hours this would last, I could divide by the number of amps the chip requires, which is 155 micro. Divide by 0.000. So that's milli. Was it 155? Yes. 155. Okay. I think that works out. Amp hours divided by... Yep. Okay, yeah, of course. Yeah. Amp hour, amp times hours. Divide by amps and you have left it. What you have left is hours, right? So I divide by the number of amps. Geez, this is a lot of time. This is a long time. Depending on the startup time, I can use this accelerometer. I can just leave this accelerometer on all the time, and I can have it wake up my microcontroller. That's a lot. Yeah, 2,850 amp hours divided by 155 microamps results in this number of hours. Is that right? That seems insane. Yeah, it's an insane amount of time. All right, well, I thought I was going to need like well, you know, I probably still need a DeWalt battery, though, because the LEDs themselves are gonna eat an amp each. So, All right, good to know this thing doesn't use a lot of juice, though. Okay. Typical startup time in milliseconds. Okay. What is this? Okay. So it's really, so if I keep ODR hertz high, the startup time is very low. Okay. Good to know. I mean, this thing is an I2C accelerometer. It's pretty bog standard simple, right? Because you are talking about acceleration. 1g equals 9.8 meters per second squared. Here's a circuit diagram. I only need 2 capacitors. This one looks optional, C1. But it doesn't really need that much else. Of course, what it doesn't show is the serial data and the I2... Where's the other one? Serial clock. Those are going to need pull-up resistors. You know, depending on the conditions, but really it's like 4.7 kilo ohms usually does it. Interesting. Okay. This is just showing what results you should expect depending on orientation. Okay. Don't care. I know how acceleration works. Okay. All right, we'll talk about I2C. So here's those 2 pull-up resistors I was telling you about. And here's the bus. So you can have multiple I2C devices. That's the whole point of I2C, is that each of these I2C devices has a different name, and the master will just squawk the name, and of course clock it too. So every time you say a bit, you're going to toggle the clock up and down. It's kind of like having a beat. So if your name is ABC, it would be A, B, C. This clapping is the clock. It lets you know to listen at that time for your name, for the next piece of your name. And on the serial data, you say like, write to sensor A, B, C, read, register 1, 2, 3. And those last 3 I just did is when the sensor would read back the data from register 1, 2, 3. Right. That's pretty much how I2C works. Okie dokie. All right, this looks really straightforward. I'm not even gonna. Yeah. So what I just said. If I'm gonna read from a slave, this is not politically correct. You're just gonna have to deal with that. All right. So here's receiving 1 byte of data. I say, you start. So I go. So I might say like do something like snap my fingers to start. Like listen up, and I say, this is the slave address. Like, write to A, B, C. So I'm going to write, and I've identified the slave's name as ABC. The slave is going to go to let you know that he heard you. Then you're going to RA. What is RA? Register address. So I'm going to say, read from 1, 2, 3. Slave's going to snap back. Then I'm going to start again. SR means repeated start condition. So I'm just going to do so. And then I say S address, which is just the register address. Read. Slave address. A, B, C. And then the slave's going to snap back. And then I'm going to keep clapping. And the slave is going to tell me some data. And then the slave is going to not acknowledge. And we're going to be done. P means stop condition. I might sit back down or something. Maybe I'll make a skit where I act out I2C communication. But yeah, there's nothing really rocket science about it. I'm going to detail how I2C works later on the whiteboard. But this looks bog standard. Should be easy peasy. This is just all the registers that control it. Registers are just special pieces of memory that hold information about how the chip is going to behave and what data the chip has gathered. You can write to the registers that say how the chip is going to behave to change the way it behaves. And you can read from the data registers to see what sort of data the slave has gathered for you. In this particular case, it's going to be acceleration data. I think we found ourselves a winner. We're going to change our power supply to accommodate 3.6 volts, but I think it's going to be okay. I think it's going to be okay. All right. This has been fun. We've chosen a microcontroller just a little bit ago in the last video. We've chosen accelerometer. I'm excited. Let's get building. Let's buy some boards. Let's buy some chips. Let's do some demos. Let's do some soldering. Let's make some things. Let's learn some things. Let's screw some stuff up. Fail early, fail often, all the time. All right. Thank you guys so much. This has been the Alex Manassa, your engineer, always here. Hit the subscribe button below, like the smash button, and have a great day.